Welcome back to the next installment of circular motion. Now that we have some of the basics of circular motion under our belt, right, things like centripetal force, centripetal acceleration, we can apply this to some problem solving. What you see on the screen is a sketch of a stopper, okay, a rubber stopper attached to a string being twirled in a vertical circle. And we want to be able to confidently measure some of the aspects of this motion, okay, both in linear terms and also angular terms. So if you'll direct your attention to the table on the screen, you see that I've set up a comparison between linear quantities and angular quantities. Let's take a closer look at that. You are familiar already with the linear quantities, displacement, velocity, and acceleration, and I've put the common units for those in parentheses. Let's look at their angular equivalents. I could measure the distance around the circle that the stopper travels, or I could measure that distance in degrees, right, or radians, right, or even revolutions, okay? Those are three quantities. Those are all angular displacements, okay? The same thing as velocity, but in angular terms, is this Greek letter omega. It looks like a W, but it's pronounced omega. Okay, those units would be radians per second or revolutions per second. Okay, and then finally, we don't concern ourselves too much with this, but acceleration also has an angular equivalent, alpha. Okay, and radians per second squared are the typical units we use there, but you're not going to see that very much. Okay, so we can keep track of circular motion either using linear quantities or angular quantities. You saw that at work on the ladybug simulation in class. All right, what we want to do now is we want to be able to confidently translate between the two. Okay, we want to be able to go from linear quantities to angular quantities and back. And the key to that is to recognize this little piece of information right here. Right, a little bit of prior knowledge we expected to bring in, and that is that circular motion, or excuse me, circumference is 2 pi r. With that piece of information, you can translate between angular quantities and linear quantities. Watch how I do that for this particular quantity here, okay, how quickly I'm twirling this stopper around in a circle. I said at the top here 2 revolutions per second, okay. Now, if we do the math down here, in this particular case, right, it's going to be 2 times pi times 0.5, which comes out to pi. Okay, in other words, the circumference of this circle, of this stopper, is 3.14 meters. Okay, if I know that, then I can easily take this right here and convert it to meters per second, right, because I know each revolution is 3.14 meters. So that would just look like this. 3.14, right, about a second, that's 6.28 meters per second, which is the velocity. I've just translated or converted from angular velocity to linear velocity. Two other terms you came across in circular motion in the ladybug revolution is the term frequency, okay, which you see right here, and the term period. Okay, so period versus frequency. Period is simply how long it takes for the object to make one revolution, right, which is what we would call one cycle. Okay, well, think about it. In this particular case, if there's 2 revolutions every second, okay, that means 1 revolution only takes a half a second, right? What we get here is a nifty little relationship, which is that the period, t, is the inverse of the frequency, okay? So if I go 1 over 2, right, I get that the period of revolution is a half a second, okay? So if the period of a revolution is half a second, that means it'll do 2 of those every second, right? Half and 1. It'll be 1 second, and a revolution for each of those is 2 revolutions per second. So period and frequency, we say they are inversely related. In fact, not only are they inversely related, they're inversely proportional, right? As one goes up, the other goes down by the same factor. The next thing we want to do is look at the nature of this vertical circular motion a little more closely. Okay, I want you to imagine, I'm going to switch screens now. Okay, same example, new screen. I want you to imagine doing this yourself, okay, and think about how it feels as you spin that stopper or any object around at the end of a string. Okay, I think you'll realize, and maybe we can do this in class next time, but I think you'll realize that there are times when the string is pulling on your hand harder than other times. Okay, and I want to use free body diagrams in Newton's second law to show you how we know where those places are. Okay, we're going to compare the tension in the string at the bottom of the circle to the tension in the string at the top of the circle. So what I'm going to do is pause the video and draw two different free body diagrams, one for each of those two locations. Okay, let's look at these a little more closely. You see at the top here, this is going to be the tension, okay, from the string. I'm going to have to call the string the rope. So we'll say on the stopper by the rope. Okay. So at that top point, the string is pulling down on the stopper, and of course the earth is pulling down on it, the weight here, right? Now look at the scenario at the bottom, however. Okay, we still have the weight, right? That hasn't changed. The interaction between the earth and the stopper hasn't changed. However, now the string has to pull harder up on the stopper in order to maintain circular motion. Okay, so this label is the same here on the stopper by the rope, but notice that the tension has changed. Okay, because remember, to move in a circle you need to have an unbalanced force toward the center of the circle, and that's not going to happen here unless the tension exceeds the weight. Okay, so I'm going to write this now in symbolic terms, in terms of F equals ma, so you can see mathematically that the tension must be greater on the string at the bottom of the circle than at the top. Watch how I do this. A lot of you are still struggling with this, but it's a key skill in this class, which is translating your free body diagram into the F equals ma equation. So all I'm going to do here is replace this with the forces in my free body diagram. So I'm going to write the following. Ft plus Fw equals ma. Okay? Actually, that A in this case, because it's circular motion, becomes mv squared over r. Okay? And then I can solve this for the tension. Okay, I'm simply going to, we'll say tension equals mv squared over r plus, and remember that the weight of an object is mg. Okay? All right. Okay, a little math mistake here, right? When I move something over, I have to subtract from both sides, and I added, so that was a boo-boo. Let's fix it. It's going to be like that, okay? Because when I move this weight to the other side, I subtract it from both sides. Let's do the same thing for the bottom, okay? You're going to see the equation looks similar, except now the tension is going to be positive minus the weight, which is negative, okay? And when I solve this for tension, I see that this is now negative, so it's going to be positive on the other side. Okay, you can see that this quantity, right, is bigger than this quantity here, right? Because you're in the bottom you're adding the weight, and the top you're subtracting it. So it shows you that the tension at the bottom is in fact greater. The last thing we're going to look at is something called the critical speed. Okay, the critical speed is the minimum speed at which you need to spin the object in order to keep it moving in a circle. Again, and you can try this if you have something that you can twirl around, but if you spin something slower and slower in a vertical circle, you're going to notice at some point that as it approaches the top of the circle, it's just going to fall out of the circle. Okay, this would be the same thing as if you're going in a vertical loop on a roller coaster, and the car's not going fast enough, and then you fall out at the top, right? Very unfortunate event. We don't want that to happen. We want to know what's the minimum speed that I need to maintain to keep moving in a circle. Okay, that's called the critical speed. So we're actually going to use the same equation from before. Okay, F equals ma. I'm going to set that up again right on the screen. Okay, think about what happens as you twirl that object slower and slower. Think about what happens to the tension in the string. Okay. What you'll notice is that the tension gets less and less, and when that object falls out of the circle, the rope or the string goes slack. Okay? What do you think the tension is when the string goes slack? Exactly, it's 0. Okay, so the way that we're going to solve for the critical speed, okay, is we're going to set tension equal to 0 in this equation right here. All right, so that would be 0 plus mg. And then here we'll put a little c for critical, okay, or sometimes they write crit, like so. And what we need to do now is just solve this equation for v, and we will have our answer. I'm just going to do it symbolically, okay, with symbols instead of numbers. You'll notice there's an m on both sides, okay? Then I can multiply, I can cross those out, divide by m, and then multiply both sides by r, gr, like that. And then I'm going to take the square root of both sides to get rid of that square. I get this little equation right here, okay? That's the critical speed for this particular object. Let's plug some numbers in. This would be 9.8, right, meters per second squared, times, in this case, the radius. And then we square root all that. And let's see what we get. 2.2 meters per second. Okay, this is the minimum speed which we need to spin this particular object at this radius to keep it moving in a circle.